These are the solutions for the Module 5 problems for students. Problem number 1, well, even before problem number 1, we're given a solubility versus temperature curve for 5 different compounds. Problem 1 says, what mass of barium nitrate will dissolve in a liter of water at room temperature? So we need to determine the solubility of barium nitrate from the curve and see where it crosses the line at, quote, room temperature. All right, so here's our set of curves. We can identify the barium nitrate by the green line with the green triangles. That's what barium nitrate is in our legend. So the first thing we're going to do is figure out that room temperature, which would be roughly 72 degrees Fahrenheit. That's about 22, 23 degrees Celsius. I'll leave it to you to do that conversion, but we can just draw a red line, a vertical line, which establishes where our temperature is, and see where it intersects with our barium nitrate curve. And you can see that's where it intersects, and so our value is roughly 10 grams per 100 grams of water. All right, so 10 grams dissolves per 100 grams of water at room temperature, but we have a liter of water. And a liter of water has a mass of 1,000 grams. We know this because the density of water is 1. So, or 1 gram per cubic centimeter. So 1 liter is 1,000 grams. So we have 10 times as much water in our sample problem as we do from looking at the curve. So we multiply our answer by 10 and we get 100 grams of barium nitrate. All right, problem number 2. What temperature does the water have to be to just be able to put 1 pound of sodium biarsenate into solution in a gallon of water? So this is the same problem as before. However, we're going to work this problem a little bit backwards. In the first problem, we knew the temperature. We were looking for the solubility. Here, it's the other way around. We have the solubility. We're looking for the temperature, but we're still going to approach the problem in the same way. All right. We've got to convert from pounds to grams and from gallons into liters and then into 100 grams of water. So we have some conversions to do. There's 453.59 grams in a pound, and there's 3,785 milliliters in a gallon. So if we do this conversion, 1 pound is 453.59 grams into 3,785 grams of water. But the curve is given in 100 grams of water. So if we take our 3,785 grams and divide by 100, we get 37.85 of those. And if I divide 453.59 grams by that 37.85, I get approximately 12 grams. It's 11.98 something, but we can't read that fineness on our graph, so we're going to settle for 12 grams per 100 grams of water. So now we ask ourselves, all right, what temperature do I need to get this solubility? We again look at our curve. We see where the lines cross. And I already have stated the answer. It's about 6 degrees. Now, you may not know the formula for sodium biarsenate, but you can tell by the name it's got arsenic in it. And the only curve that has arsenic in it is going to be the red one. So we look at our red line, which is a fairly straight line compared to several of the others, and we look at about 12 grams. So we draw a horizontal line now that's on the axis of solubility of about 12, and we see where it intersects our red line, which is the sodium biarsenate line. and that turns out to be roughly 6 degrees. If we look at our temperature graph, it's only graded in every 20 degrees, and this is about halfway, perhaps a little more than halfway between 0 and 10, so I'm going to call it 6 degrees Celsius. All right, next problem. A 20-gram sample of methyl alcohol, CH3OH is our formula. It's dissolved in 30 grams of water, and we're asked to calculate the mole fraction. All right, so first of all, we have to have our formula for mole fraction. And they give it in this script X. It's really the Greek letter chi. Since not many people know Greek, we usually just say the English phrase mole fraction, even though we write the Greek letter chi. And the mole fraction of any compound or component in a mixture is the number of moles of that component divided by the total number of moles. In our case here, we only have two compounds, methanol and water. So it's just N sub A plus N sub B. If you had 5 different compounds, you would have a denominator that would have 5 numerical portions in it. So now we need to calculate the number of moles of each of our compounds. So clearly we're going to need molar masses. We calculate the molar mass of methanol, 32.05, water, 18.02. Now we calculate the number of moles. For methanol, that would be 20 grams divided by 32.05 grams per mole. I get 0.624 moles. And we do the same for water. We get 1.665 moles. So the fraction of methanol on a mole basis would be 0.624 divided by the sum of 0.624 plus 1.665. And that turns out to be 0.273. So our answer is E, none of these, because none of these have a numerical value of 0.273. One answer that students sometimes will choose in error would be choice C, because that's 1 minus 0.273. But that would be the mole fraction of water. So if they either did the calculation wrong or weren't sure what their answer was telling them, they might pick choice C in error. All right, problem next. A solution of hydrogen peroxide is 30%, 30.0% hydrogen peroxide by mass and has a density of 1.11 grams per cubic centimeter. The molarity of the solution is, and we have 5 choices. This is a good problem to practice our skills with converting between molarity and mole fraction. All right, we start here by assuming we have 100 grams of the solution. We don't really know how much we have. We might have 100 grams, but if we pick 100 grams, our math gets appreciably easier. We know that if we picked 100 grams, 30.0 grams of that 100 grams would be peroxide, which would make the other 70.0 grams water. So our formula for molarity is moles solute divided by liters of solution gives molarity. We use the symbol capital M. So we need to calculate both the numerator and the denominator to get this molarity. All right, so this is straightforward for moles, because we know we have 30 grams for every 100 grams of solution, and it would be the same whether we had 100 grams of solution or 100 million gallons of solution. So we take our 30 grams, we divide it by the molar mass of peroxide, which is 34.02, and they give us the formula of hydrogen peroxide at the top, so you don't have to memorize anything. You can just calculate it. 30 divided by 34.02 is 0.882 moles. Now, We don't know about water, but here we can use the density of our solution to convert from mass of solution to volume of solution. We do this through our density equation. We know that density D, or sometimes given as the Greek letter rho, which looks like a P but isn't, D, density, is mass divided by volume. If we rearrange that, volume is equal to mass divided by density. We have both of those. We have a mass of the solution, which is 100 grams, divided by the density of the solution, which is given, 1.11 grams per cubic centimeter. So we get 90.09 cubic centimeters. And we divide that by 1,000 to convert to liters, and we get 0.09009 liters. Students will sometimes ask, well, why are you using the solution instead of the water? The answer to this question is that molarity is given as liters of solution. So we have to take the volume and the density of the solution to get these numbers. All right, so now we have all we need to calculate molarity, 0.882 moles divided by 0.09009 liters, and we get 9.788 molarity, or molar. So our answer is C. All right, the next question. Calculate the molality of ethanol, C2H5OH, in a water solution prepared by mixing 50 milliliters of C2H5OH with 100 milliliters of water at 20 degrees Celsius. And they give us the density of the ethanol, so the ethanol, not solution, but the ethanol is 0.789 grams per milliliter at this temperature. And they give us 5 choices. Okay. Our formula for molality is moles of solute divided by kilograms of solution. So again, we're going to need to calculate both of those components. So as before, we can use our density formula to get mass of ethanol. The mass would be the density times the volume. We know the density. They give us the volume of 50 milliliters. So I get a mass of 39.45 grams. And this allows us to convert to moles by dividing by the molar mass. So we get 0.856 moles. Now we can do the same trick we did in the previous problem, but in reverse to get kilograms of water. But since the density of water is 1, this is a pretty easy, trivial calculation. So 100 grams of water, which is, we have 100 milliliters of water, that's 100 grams of water. And 100 grams of water is 0.1 kilogram of water. And so we can now calculate molality using our lowercase m, 0.856 moles divided by our 0.100 kilogram, and that gives us a molality of 8.56. Again, we use the lowercase m to denote molality, the uppercase m for molarity. So our answer in this case is number C. We're going to stop here. These videos are a maximum of 15 minutes long, and we're at 14 minutes. Not enough time to go further, so we'll just stop here.